Hi everyone, welcome to the fourth session of our meta-analysis in our tutorial. In our previous sessions, we mainly talk about effect size measures in single group designs. Mainly, we have seen correlation, mean, proportion, and we have also touched effect size measures in control designs. And we have actually touched mean differences. If for continuous outcomes, we have already started for control designs. And one of the topics that we covered in our last session is the mean difference. That's the raw mean difference between the groups. That means it could be between control and experimental group, or between within one treatment group. That means before and after intervention mean difference. So before we dive, so today I want to cover more on standardized mean difference. But before we dive into that, let me just give you a quick summary of what we have done last time. So last time we have said for continuous outcomes, the first thing that you need to ask is whether the scale of measurement is similar. If the scale of measurement is similar, that's the first thing that you need to ask before you decide on the effect size measure. If the scale of measurement is similar, then what you have to do is the between group mean difference. That's the raw mean difference between the control and the experimental group. If the scale of measurement is different, then you have to do standardized mean difference. If you remember, for mean difference, we have covered different effect size measures such as simple analysis of final values, simple analysis of change scores, and ANCOVA adjusted mean difference. So today I want to cover more on standardized mean difference. And standardized mean difference is the difference in means between two independent groups, which is standardized by the Pauli standard deviation. You mainly divide the mean difference, the raw mean difference, and then you just calculate the raw mean difference, and then you calculate that raw mean difference by the Pauli standard deviation. That's what you need to do. So the first thing that we need to do is between group standardized mean difference today, and then there are other things that I want to cover. That means within group standardized mean difference. That means when a study has before and after intervention, but it doesn't have any control group or something. That's what we need to do. That's within group standardized mean difference. That's mainly you use it mainly within before, after, or pre-post studies. You can actually use within group standardized mean difference also for control group designs. That means treatment and control. That means you calculate the within group standardized mean difference within the treatment group, and then you can also calculate within group standardized mean difference within the control group. After that, you can subtract the within group standardized mean difference within the treatment group, subtract it, and then you subtract the within group standardized mean difference in the control group. And that means you get the difference of differences in standardized mean difference. The last I want to cover is within group mean difference. If you remember last time, we already talked about mean difference, but these two concepts, they are nearly, they go together. That's why I try to group these ones. I try to put together. But again, the within group mean difference is the raw mean difference within a certain group. That means within a treatment group or within a control group. Yeah, so between group standardized mean difference, that's what I want to cover today. So standardized mean difference is actually another more popular method of effect size measure for continuous outcomes, and it's defined as a difference in means between two independent groups and standardized by the pooled standard deviation. That means what you need to do is you create the mean in experimental group minus the mean in control group divided by the standard deviation, which is pooled for the experimental group and for the two standard deviations. So you basically pool standard deviations. So you remember we have seen pooled standard, how you calculate pooled standard deviation from our last session. So let's say if you're doing a depression trial on depression, and you may have many studies, maybe 7 or I don't know, more than one studies, and you have many different scales. So you may have Hamilton depression scale, and 5 other studies may use Montgomery Asberg depression rating scale. It's kind of two popular. I don't work in depression research. Don't quote me, but these scales are kind of very popular scales at least in depression research. So the problem is, if you want to do a mean difference, that means a raw mean difference, the amount, the level, the depression, the measure that Hamilton depression scale gives you is a little bit, it's different from the Montgomery measure. So that means you cannot really combine it. To combine it, what you need to do is you have to standardize it, or at least you need to scale it. That means you need to rescale. Between these two scales, you need to find a way to standardize it. And that's by dividing with a pooled standard deviation. And this actually is called dimensionless effect measure, because you basically remove the dimension. That dimension is by this scaling. You basically remove the dimension by standardizing it. It's actually also called Cohen's d, because it was actually originated by the statistician Cohen, so they call it Cohen's d. And there are kind of rule of thumbs for standardized mean difference. So, for example, if the standardized mean difference is 0.2, they call it has a small effect. But if the standardized measure mean difference has about 0.5, that means treatment that you are, or your interventions has moderate effect. But if it is more than 0.8, that means the intervention has really large effect. So between 0.2, less than 0.2, from 0 until 0.2, it's a small effect. And then from 0.2 to 0.5, you call it moderate effect. And then everything after 0.8 is actually a large effect. So you can basically use this depending on how your pooled standardized mean difference shows, and that means you can simply say whether your standardized mean difference, I mean whether your intervention or whether your pooled standard mean difference has a strong or small effect based on the values. So for the parameters you need to calculate the parameters that you need to calculate or to do standardized mean difference meta-analysis. There are some parameters, and that for those parameters, what you need, the first function you need is meta count, and meta count requires these functions. And the first one is number of participants in the experimental group, and then of course, just as we did last time, it's the same, the mean of the outcome variable in the experimental group. Then you also need the standard deviation of that mean. The same is true for the control group, and then you simply pass them with this meta count function as the end. You need to decide the effect size measures that you have standardized mean difference. We'll come to that. I will show you in my tutorials in the coming sessions. But let's just focus more on understanding the effect size measures in the sessions. So before we dive more, let me just show you a quick tutorial on how to calculate standardized mean difference and how to calculate the pooled standard deviation. Probably the pooled standard deviation we may not see it because we have already covered it last time. So let me just launch my R, and then we will see some of the basic things that we need to calculate standardized mean difference. So let me just calculate a few things here. Let me just assign some values. Let me call x1 as that means the mean of group 1. Let me give it 50, the mean of group 2, and then let me assign it 60, and that means there is a row mean difference of 10. Actually 60 minus 50, that's 10. And then let me just give it standard deviation of 1 to be 10, and again let me also give it standard deviation to be as again 10. Let me just define the same, and let me call it the number of samples for the control group as 100, and number of samples again for the second group for the intervention group. Let me just give it 100. So to calculate standardized mean difference, the first thing you need to do is you have to calculate the mean difference, and the row mean difference, that's what you need. The row mean difference would be x2 minus x1, that's what you need, and then you have already got the mean difference, and then after that what you need is you need to calculate the pooled standard deviation. That means pooled, let me give it standard deviation pooled, and for that we already have a formula, and we have already created a function last time. This is a formula how you calculate the pooled standard deviation, and we have already converted that formula into an R function, and that function needs all these parameters. That means the sample size of n1, and I mean the first group and the second group, and it requires a standard deviation of the first and the second group, and that means this is the formula that we need. It's already there, so we will just use that standard deviation formula. That's what we need. And probably let me rerun this, and maybe it's not the function is not there, so I know what the function should be there, and let me just call that function s-pooled. And for s-pooled, what we need is n1, that means 600, and n2 is also 100, and s1 is 10, and s2 is also 10. So now we already have the pooled standard deviation. So now let me print it, and let me just calculate the effect size measure actually. So the standardized mean difference would be the mean difference, the row that we calculated just here, divided by the pooled standard deviation. That's actually our pooled standard deviation. This is what you need, and then after this, let me write it again. And now we expect about 1, actually, it should be about 1, because 60 minus 50 is 10. The pooled standard deviation should be also 10. I don't expect it to be far away from 10, or maybe far less or far bigger than 10. So the standardized mean difference should be 1. But let me just look it. So now you see the standardized mean difference is 1. In other words, you can also use this if you don't want to calculate all of these, especially if you have many studies. You may not need to calculate it this way. Instead, I mean, you can do it this way. It's much better actually. But otherwise, you can also use this package called effect size package, and this effect size. And then afterwards, what you need is you simply need the effect size. Maybe let me load the library first, and then I will find the function. Otherwise, I may have difficulty. Okay, now let me just use the effect size, this mean. There are many different functions from this effect size function. So effect size package, I mean. So effect size mean standard deviation. This is what I need, the mean standard deviation. So that means, or maybe let me just see it again. Actually, and then see what are the parameters. So actually, it's showing me. But let me just print it and see what are the parameters of this effect size. Alright, so I can simply scroll up with mean, and I will get standard observation. So it's really giving you the standardized mean difference, I would say. So Yeah, so let me just use that formula, and that formula requires all of these values, basically all of them: x1, x2, sd1, sd2, and then n1, n2. So let me just, because the way it's grouped is group 1 mean, and that means it's 10, no 50 actually, because we defined it to be 50, and then group 1 standard deviation, actually group 2 mean. Let me just define that before I define the others, and then group 1 standard deviation, and that means it was 10. And it's really boring kind of parameters the way they wrote it, but that's how the function works. And then group 2 standard deviation, that is again 10. Group 2 standard deviation is 10. And then afterwards, what we need is group this is group 1n and group 2n. Group 1n is 100, and group 2n is group 2n, that is again 100. So we should be able to find the same standardized mean difference as we calculated before. That means it's 1. So let me rerun this, and then let me see. Yeah, so it's actually giving us more values. So the effect size it's showing actually -1. Mean and standard to effect size d, actually, because it's yeah, so it's calculating from x1 to x2, but so you need to be very careful in this case, very careful in a sense. I mean, the default function is obviously group 1 minus group 2, but if you want to put it, so the sign is very important. So you need, if you want to report let's say the intervention actually reduces some kind of, let's say depression. So the intervention reduces depression, then you have to use this negative sign. That means you need to calculate from the treatment group minus the control group. But if the intervention actually is aimed, or if the intervention is actually increasing, for example, if you think quality of life is a positive outcome, so it's usually positive outcome. So the bigger it is, so the better the change. So that means you always have to be very careful how you define the order of these variables, like group 1, group 2. Otherwise, everything should work exactly as that is. And then it gives you standard error. Of course, if you want to calculate confidence interval, you need these values, the standard error or the variance. That's what you need. It's already calculated. Actually, we already have the lower and upper confidence interval. That's again, if we do the confidence interval, we have to go more steps, because we have to calculate the z-score, and then once we get the z-score, we can apply the variance formula to get our 95% confidence interval within with this alpha over 2 or something. So that means, so that's what you need: standardized mean difference plus or minus this one minus 1 plus or minus 1.96, and then the square root of that. I mean, times this variance value. That's actually the formula that we need to calculate the confidence interval. In the next sessions, actually, we can use the manual way of, instead of using the package or something. We will cover that in the coming sessions. Yeah, so that's as I said, for the meta-analysis of standardized mean difference, you need a meta-cont, and then you actually need all these values. And then you just need to supply your data and define some of the parameters, and then after that, you should be fine to get your pooled effect sizes measures. Yeah. So now let's dive to the next one. That means it's Wisen group standardized mean difference. So the Wisen group standardized mean difference is usually the before, if you have a before after intervention. For example, if you want to, let's say, if you say physical activity improves depression, so you start before the start of the intervention, you measure the depression level, and then at the end again, after the end of maybe 3 months of physical activity, and then you try to measure depression again, and then you see the difference between the beginning and the last, the intervention, the mean at the intervention in the point minus the mean at the beginning of the intervention. So that means you what you do is means at the 2 intervention points they are not independent. That's a problem in within the group, because the mean at the end of the intervention is actually related with the mean at the beginning of the intervention. So the mean at the beginning predicts actually the mean at the end of the intervention. So that means the two means are not independent. They are not independent. That's actually problematic. So that's pre-post interventions. As I say, depression. So if you have depression, what you need is you need to have this standard mean difference within group standardized mean difference, and then you have this for the weight loss intervention. I mean for the standard, this actually interchanged. This has to be here. So that means for weight loss interventions, because weight, if it is standardized, that means it's usually measured in similar scale. Maybe it's measured in kilograms. All studies may report in kilograms. Then you are fine to use the raw mean difference. That means the mean difference within mean difference. That means the mean at the intervention in the points, that means at time 2 minus the mean at the beginning of the intervention, that means at time 1. And what you need is for the depression, because depression could be measured in different scales, then for the depression, what you need is you need to have this standardized. Actually, let me move this, because it's not what this was supposed to be here, and this is supposed to be here. Yeah, so that's how you calculate the standardized mean difference within. It's actually the same principle from what we have seen with between group standardized mean difference, except that this is just within a group, and it really depends on the initial measure. So some people suggest to use, actually the people say there are many different ways of calculating this standard deviation instead of using pooled standard deviation. Some people recommend we don't have to use this pooled standard deviation because they say the interventions are, I mean the two before after the mean, they are not independent. So using the pooled standard deviation may be erroneous. At least it may not be that precise. So people suggest there are actually five different ways of calculating this standard deviation for this part, not the pooled one, but there are many suggestions. Anyway, some people suggest to use standard deviation at the first, that means a baseline standard deviation instead of the pooled standard deviation, because they say the standard deviation is not going to be much affected by the change of by the duration. So that means they suggest to use SD at T1 instead of the pooled standard deviation. And some may say, okay, let's use a pooled one, but there are also other methods to calculate the standard deviation for this for the standardized mean difference, so within group. The reason for this is actually that the reason that we need to use SD at T1 is less likely. They say SD at T1 is less likely be influenced by intervention effects. They say it's not. I mean, that's what they have shown. At least some papers they say it's not likely influenced by the intervention effects. Anyway, these are the way you calculate the standard errors, because this is what you need if you want to calculate the confidence interval of that or the confidence interval of this. So that means you need a standard error for mean difference within. For this one, this is the formula that you need. The problem is you need R again, that means correlation value, which usually is not reported in studies. Good luck with that. That's problematic. And then again, standard error for the within group standardized mean difference. This is again the formula that you need. Again, it requires the pre-post correlation. That's the pre-post correlation. But again, this is again problematic in many of the randomized control trials or pre-post studies. This pre-post correlation, it's just not reported. So what you can do is you can assume. What you can assume is, let's say if you have 10 studies, if 2 of them or 3 of them have already reported standardized, this pre-post correlation value. If you have 10 studies to meta-analyze and only 3 of them reported this R value, then what you can do is you can average the 3, and then let's say if one reports 0.5 and then the other one reports 0.6 and then the other one reports 0.7, then 0.6 plus 0.5 plus 0.6, it's 0.18. Then you average it, it could be 0.6. Then that means you assign 0 of correlation, an R value of 0.6 for all the remaining trials. That's what you can do. But again, if you have necessary data to recalculate it, as we have seen it, as I have shown you in the previous tutorial, you can again recalculate it. But again, it's very unlikely that you get those data. Otherwise, there are also people who just assume 0.5. They simply assume 0.5 and then simply rule the whole thing with 0.5. Yeah, but this again, if you are really off point in measuring that R value, then your effect size will be maybe erroneous. So that's what you need to be very careful. Anyway, this is standard error measures. This is standard error values to calculate for within group mean difference, and then within group standardized mean difference. They are really complicated. But yeah, good luck with that. In the worst case, you just assume 0.5 and then hope that everything is fine. Yeah, as I said, standardized mean difference is a good technique to actually deal with effect sizes measured by different scales. So it's kind of a good way to standardize different scales and then still be able to combine in meta-analysis and still deal with the heterogeneity of between the scales. But the problem is standardized mean difference is not a magic bullet. It has its own limitations. So the one is if, for example, if the size of the one limitation is the size of the standardized mean difference actually depends on standard deviation, because if you remember, the pooled standard deviation is the standard deviation is at the denominator. So that means so the size of SMG divides, because it's MD, mean difference, divided by standard deviation. So that means you are if your standard deviation is very large, so your standardized mean difference will get small, and if your standard deviation is small, especially in your large trials, this value gets smaller, then your standardized mean difference gets high. So let me give you one example. Think of 2 studies. One is large and one is small. Small and large means one has high number of sample and the other one has again a small sample size. So they use the same instrument reporting exactly the same mean difference. Let's say they are depression. I gave you one example. It's depression. So they use Hamilton depression scale. And then let me give you these 2 different means. So the mean 1, this is actually supposed to be mean 1, so that means 10, and the mean 2 is again 10, but the only difference is the standard deviation. So standard deviation, the mean, this one has a large sample, so that's why we have a small small standard deviation, and it's 2. And this one has a small sample size, and it has high dispersion. So that means it has a big standard deviation. So that means 5. So if I ask you to calculate standardized mean difference, what you can do is you divide 10 divided by 2. This one has a standardized mean difference of 5, but this one has a standardized mean difference of 10 divided by 5. So that means it's going to be 2. You know that the effect sizes are exactly the same, but when you do standardized mean difference, one is actually twofold of the other, which is problematic, because you already know that, you know that these studies, they have exactly the same effect sizes, but because we have to standardize things, that means the effect sizes are getting different. So in this kind of scenarios, in this kind of situations, standardized mean difference is problematic. So it may skew your results in a way because of your sample size. Yeah, so that's all what I want to talk about today. Next, I will continue further, especially on categorical outcomes, and we go deeper into things like risk ratio, odds ratio, hazard ratio, and then once we have that, we will dive more on the practical aspect of meta-analysis. We will talk about fixed effects and random effects meta-analysis. That means we'll be more on the practical aspects of meta-analysis. Yeah, that's all for today. I hope you will continue following this channel, and yeah, that's all for today. Thank you for watching.